This is the first video on Chapter 18, the squeeze theorem. So first of all, I want to draw a picture of what the squeeze theorem actually says. So it says that if the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to L, and then we have this function h that is between f and g. Then the limit as x approaches c of h of x is also L. So this is called the squeeze theorem. H is squeezed between f and g, and f goes to L, g goes to L, so h goes to L. Sometimes this is called the sandwich theorem as well, because h is sandwiched between f and g. But this is the idea. Now, the squeeze theorem itself, conceptually, isn't so hard. It's a fairly simple concept to understand. The examples that you use the squeeze theorem for, however, tend to be complex. So here we're going to look at example 149. I will do example 148 in the next video, but example 149 I think is a little bit easier than example 148, so I'll do example 149 first. G of x, it's a piecewise defined function. It's x if x is a rational number, and it's x squared if x is an irrational number. So this notation here, this says x is in the set Q, where Q is a set of rationals, and this says x is not in the set of rational numbers. So that means it's irrational. Now the thing about the rational and the irrational numbers is they're everywhere. So they're what we call dense in the real line. That means between any two real numbers you can find a rational number, and between any two real numbers you can find an irrational number. So proving that is beyond the scope of this course, so we don't prove that. It's not incredibly hard, it's just a little time consuming. But just keep in mind between any two real numbers there's both a rational and an irrational. That means when you make a piecewise defined function in terms of the rationals and the irrationals, it can jump all over the place, like this one does. And so g of x is x if x is rational, so that's why we have this dotted line. So this is the line y equals x right here. So these represent the function values of the rational numbers. But if x is irrational, then we square x. And so those points appear on the parabola. And so we have the parabola y equals x squared. Part of this parabola is the graph, part of the graph of this function, and part of this line is part of the graph of this function. And so example 149 asks us to prove that the limit as x approaches 0 from the right of g of x is equal to 0. And so we do that by noticing that, okay, between 0 and 1, the line is above the parabola. So as we get close to 0 from the right, x is greater than x squared. And so this function is sandwiched between x squared as a lower limit and x as an upper limit. If we take the left-hand limit, and we weren't asked to do that in this example, the parabola is above the line. So now the line's the lower limit and the parabola is the upper limit. The squeeze theorem is valid for left and right-hand limits. So the limit as x approaches 0 of g of x is actually 0. But we would do that by taking a right-hand limit using the squeeze theorem one way, then taking the left-hand limit using the squeeze theorem another way. The only two places that this function has a limit is at 0 and at 1. But the example 149 was simply to show that the right-hand limit at 0 is 0. And I wanted to just give you the graph of this function to give you an idea as to what this looks like. And in the next video, we'll look at example 148.